All right, today we're going to learn about concavity. Concavity is how a curve bends. So if you look at the graph that you see right here, you can tell that the graph is increasing on specific intervals and also decreasing on specific intervals. But looking at that graph, you can see that there are different bends that are going on. So in the first question, we want to know on which intervals is the graph of the function concave up. So concave up is how you want the curve to bend up. So if you want to remember concave up, it looks like a cup. So it'll go like that. And concave down looks like a frown. So what we want to do is look where this graph is concave up. So if we were to highlight where we think that there's a section of the graph where it looks like it's going up. So it kind of looks like it's starting here. It's bending up there. But then what's unique is right at the origin, it still looks like it's still bending up there. So what we would say is that this graph is concave up on the open interval 0 to infinity. Then if we wanted to know where the graph was concave down, we want to try to look like it's a frown, and that looks like it's going from negative infinity to 0. All right, so there's your definition of continuity, just your technical, formal definition. But if we do read it, we want to basically look at the graph of f is concave upward on an interval if f prime is increasing on the interval. And if you have concave downward on an interval, then that means f prime is decreasing. So that's pretty important to highlight. So if you have your highlighter, take that. F prime is increasing, so that means you have concave up and concave downward if f prime is decreasing. So it's very important that you know how a graph is changing as far as increasing and decreasing, and that can tell you other things about its derivative. So if we look at example 1, you have those two stocks of two companies, A and B, and both of them went up in value, but both currently sell for $75. So we want to know which one is the better investment. So take a look at those and determine which one is the better investment. And hopefully you said that the better investment is stock B. And then we want to just know of the little thing Y. So you can write this down. All right, so go ahead and copy that down. And you'd probably want to pause your video, write it down, and then have a read. Try to absorb what is written. All right, so the next section that we have there, we're looking at the graph in figure 1. And we just want to recognize that a function can decrease while its derivative is increasing. So if you look at figure 1, the derivative of f prime is increasing. And what we can say is, since the tangent lines are getting less steep, their slopes are becoming less negative. So in theorem 3.7, that's your test for concavity. If you have a function whose second derivative does exist, you have those two following conditions. So if the second derivative is positive, then f is concave upward. And if the second derivative of f is negative, then f is concave downward. All right, so the one thing, this little note up at the top that just says concavity is not defined for a line. Therefore, a straight line is neither concave up nor concave down. For the most part, we will deal with non-horizontal lines. So looking at this little chart here, we have 4 boxes that we want to analyze. And if you have an increasing and a concave up function, that would mainly look something like that. So that function there is increasing as moving from left to right and is also concave up. So by looking at that, we can say that f prime is greater than 0. And since it's concave up, the second derivative will also be positive. So looking at the slopes of the tangent lines, which is f prime, you can tell that they're all positive. And then by the test, the theorem for concavity, the second derivative is positive. So now if we looked at an increasing and concave down function, so going from left to right, you're increasing but concave down, you would have a situation like that. We can tell that the f prime is positive. So all the tangent lines that you would draw along this curve are going to be positive slope. And the second derivative is negative because we want a concave down function. The third case, we have a decreasing and concave up. So decreasing means going from left to right, you're going down, and we want concave up. So a decreasing function means that f prime is negative, and a concave up function is f prime is positive. And then we have a decreasing function, concave down, and hopefully by now you can tell that a decreasing function means that the derivative is negative, and a concave down function means f prime, double prime, is less than 0. So as a curve bends in a different direction, either changing from concave up to concave down or concave down to concave up, that's a specific point, and that point is a point of inflection. And a point of inflection is found the same technique that you would find a critical number, but you focus on the second derivative. So you're going to set that second derivative equal to 0 and also find where the second derivative is undefined. So it's basically repeating the same process as finding a critical number, where you'd set the first derivative equal to 0 and also find where the first derivative is undefined. But if you're talking about the second derivative, we would then find a point of inflection. So if you look at the couple graphs that follow, we want to see where the curve bends differently, where it changes from bending up to bending down and vice versa. So take a look at the first graph that you see here and focus on the x value where you think you would have a different bend, and it looks like it's going to be at x equals 0. So at x equals 0, a point of inflection exists. So if you look at the second graph, take a look at it, see where the x value, where you're changing from concave down to concave up, and that looks to be at x equals 1. So you can say a POI, which is point of inflection, at x equals -1. And then the last one looks like there's a point of inflection at x equals 1. All right, so that's how you would find it graphically. Now what we want to do is actually find a point of inflection algebraically. So if we look at example 2, it says find the points of inflection of f of x equals cosine x on that closed interval. So in order for us to find a point of inflection, we want to get to the second derivative. In order for us to do that, we want to find the first derivative first. And f prime is equal to negative sine of x. Then take the second derivative, which is going to be negative cosine x. And that's where you set the second derivative equal to 0. And the two x values in which cosine is equal to 0 are pi over 2 and 3 pi over 2. So in order for you to find whether each one of those are a point of inflection, we want to take those critical numbers from the first derivative, so those possible points of inflection, and put them on a sine line, but for the second derivative. This will determine if you have a sign change on the second derivative. So plug in a test value for f double prime that's on the left side of pi over 2. And what I'll do is I will test 0. And when you do that, you get a negative result. If you test a value in between pi over 2 and 3 pi over 2, you can test pi. That'll give you a positive result. And then from 3 pi to 2 pi, let's test 2 pi, and you'll get a negative result. So whenever the second derivative changes sign, as you can see here and here, those two x values are points of inflection. So what we will do is, I kind of ran out of room, but I will write the points of inflection here. So POIs, we want the point, so the first point is pi over 2, and then in order for you to find the y value, you have to plug it back into the original function. So the cosine of pi over 2 is 0, and the second one that we would have here is plugging in 3 pi over 2 into the original function, and that leads us to 3 pi over 2, comma 0. And remember, in order for you to find those points, you have to plug the x value back into the original because they are points on the actual curve. So go ahead and graph the original function cosine of x on your graph there, and then see if you do have a point of inflection at those two x values. So I have my cosine curve, and as you can see at x equals pi over 2 and 3 pi over 2, those are your points of inflection. This is your concave up part, and then this is your concave down and concave down. And then for our last example, we again want to find the points of inflection, and then we want to state the intervals of concavity on f of x. And it says justify your response. So the AP does use this terminology, justify your response, quite a bit. So we do have to have a reason. So let's go ahead, find that second derivative. So feel free to do that on your own. And once you find that second derivative, you can set that equal to 0. And we need to solve for x. So when we're solving this type of equation, we need to factor. And once you have that factored, set both of those factors equal to 0, and you can find that x equals 0 and x equals 1 are possible points of inflection. And I do say possible points of inflection because now we have to test them on a number line to see if you have a sign change in the second derivative. And that's what we're going to do here. So you take those two values, 0 and 1, and we want to have test values on each side. So from negative infinity to the 0, if you plug in a value, say negative 1, into f of x, you'll end up with a negative result. If you do the same technique from 0 to 1, take maybe possibly 1/2 and plug it in for f of x, you'll notice that that's a negative value. And then from 1 to infinity, we should have the same sign for f double prime, and that's going to be positive. So I just took negative or positive 2 and plugged it into the original function and got a positive result. So as you can see, we only have one sign change on f double prime, which means you only have one point of inflection. So we're going to state that point of inflection. So that's going to be a POI at 1. And once you plug 1 into f, you'll get negative 1. So there's your point of inflection. And it says justify. So if it didn't, we need to justify this. Now, how do you know you have a point of inflection? We say because f double prime changes sign at x equals 1. And you need this part right here. This is very, very important for the AP exam. We need to make sure we're talking about a specific x value. So please make sure that you're saying at x equals 1. It's very, very important. Now you can say that f double prime changes from negative to positive, but you don't have to. You can specifically just say it changes sign. And then we have to determine our intervals of concavity. So as we said before, f double prime, if the second derivative is negative, then we have a concave down function on f. So we'll say f of x is concave down on negative infinity to 0 and 0 to 1. We have to make sure we split these intervals up because specifically at 0 you're neither concave up or down because that is the value that would make the second derivative 0. And the reason why we know that f of x is concave down is because f double prime is negative. And you have to say where on those intervals. So the intervals that you're giving are answering the part where it says state the intervals, and then after because is answering the justify part, and that's why it's important to say on those intervals. So now if we look at the concave up part, you say the exact same thing, but we use f double prime as positive. So f of x is concave up on wherever f double prime is positive. So as you can see, that's from 1 to infinity because f double prime is positive on that interval. All right. Thank you for listening. If you have any questions, then please ask them next class. Work with each other and have a great day.